We'd next like to use an example from chemistry. Again, if you look on in the sidebar here, you'll see a variety of CSCS investigations. So we're going to open up the chemistry link here and look at composition of biological molecules. So whether you're looking at DNA or kind of the chemistry of fruits and vegetables, or diatoms, or the pharmaceuticals, whether you're looking at plant species or molecules of hemoglobin, all of these things are biological molecules, molecules that make our systems run. So our foods that we eat, to the the variety of different things that we consume, all of these things are composed of biological molecules or interact with biological molecules. So whether we're talking about neurons or we're talking about rainforests, whether we're talking about parrots and animals like this or mammals, all of these things are composed of biological molecules. And typically, in a typical biology or chemistry class, we talk about those molecules and have the students memorize their formulas and their composition. But CSCS allows us to very quickly do kind of a collaborative analysis of what those molecules are composed of. So the question for this activity is, what are biological molecules composed of? In other words, which atoms are they made of? Are they made of all the various different atoms in the periodic table, or just a portion of them? So in this case, every student is going to pick a biological molecule. So here's some examples of some biological molecules that they could choose from. So we've broken down into amino acids, to sugars, to pharmaceuticals, hormones, nucleic acids, and vitamins, and just miscellaneous ones. And they'll be familiar with some of the names of these. If they scroll through, they might recognize that sucrose right here is simply table sugar, or they've probably heard of codeine as a pharmaceutical painkiller, and so forth. And so if they want to look at the structure of those molecules, they can do so by going back to the activity page and then looking at the next one, which is going to be 3D Chem. So let's just choose that we want to look at sucrose. So as we scroll through here to find sucrose, let's see if we can find it right here. Well, so there's sucrose right there. So you can click at sucrose, and a molecule comes up. And in this molecule, we can actually open it up in 3 dimensions, and the students can get an idea of what it looks like as it's, well, obviously kind of some artist's rendition of what the spatial representation of the atoms are. So by looking at different models, they'll realize, okay, that happens to be exactly the same molecule as this wire diagram, as this ball and stick diagram. And then they can also look at turning the labels on so they can see what those atoms are. So if they are confused about what the colors represent, they can look here. And so we can see here that that hydrogen is labeled as white, carbon is black, and oxygen is red. And again, those things make some sense. Red for fire, because oxygen is necessary for fire as an oxidizer. Black for carbon, because coal or graphite is black. And hydrogen is invisible, so the closest they could come is white. And those are pretty standard colors. You'll find that nitrogen is blue, and then there's other colors for different molecules. So the idea in this case right here would be to count up the number of each atom in this molecule. So if we're to look here at the oxygens, for example, we'll try to position it in such a way that we can actually count all of those oxygens. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this has 11 oxygens in this molecule. If we were to count the carbons, we would just count the gray ones. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 carbons. And finally, we count all of the oxygen, or the hydrogen. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So we missed a couple on the back side right there. We can see there's 21 and 22. So once they've rotated around in 3 dimensions, they've caught all of those, they can then go ahead and enter them into the database. So they'll return to the page here and then enter this data into a form. So in this case right here, I'll just put my name here. Okay, so this is Norm. And we'll scroll down here, and the molecule that I've chosen is sucrose. And that would be a type of a sugar. And in terms of the hydrogens, at least I counted 11. And I'll scroll down here to the oxygens. And I counted 12 of those oxygens. And actually, I'm sorry, that was 22 hydrogens. And 12 carbons. So after we've entered that information, they'll scroll to the bottom and they'll see submit. Now, very quickly, everybody in the class could do this, and depending on the number of students in the class, you can quickly get 30, 40 data points. And the students could each required to collect 3 or 4 molecules, doesn't matter. But now we can actually do some analysis with this. So if we look back here, the next thing is that the students are supposed to examine the raw data. So they can go back and they can look at the raw data for their class. When they click on the raw data here, they will see, wow, this is the whole class data, not just mine. We see that all those elements down here, 15 through 22, aren't even represented in these biological molecules. Just a few are. And we can see that hydrogen, the blue one right here, is the most abundant of those molecules. See that carbon, this one right here, is the next most abundant. Then the third most abundant is oxygen, and finally we see nitrogen. Again, I'm matching the colors across here. Well, we could then take that same data, and that data was actually coming originally from these form responses. So this is the data that people entered. You scroll across, you can see that the data table shows the numbers of carbons, hydrogens, oxygens, nitrogens, and so forth that were put in here. And what we did is we simply looked at the calculations here and made a separate tab for this, in which we can now look at kind of a summation of this data. So to do that, you simply press a plus there, and it'll generate a new tab, and then you can start to enter in the appropriate calculations. I'll delete this for right now. And so looking at the calculations, we took the category headers, just copied them from the other page. And then in terms of the number, notice the formula there. It's going to sum the form responses. In other words, going to the form responses tab, which is where the data originally came. And we're going to take the range from E2 to a very large number, just basically the first number to as many as would ever be entered. And so that's going to give us a quantity, and that's where this 80 is. In other words, of the molecules that have been currently entered into this data table, 80 of them, 80 atoms of hydrogen are represented. So that's where we're going to get this raw data from, the number of molecules. You can look over here, and indeed there are 80 hydrogens. That's what that's coming from. So the molecules that we've examined to date, in other words, the ones which you see over here, which would be citric acid, valine, histidine, isoleucine, acetaminophen, aspirin, and sucrose, those ones have 80 hydrogens collectively, and 52 carbons, and so forth. Now, we can also do further calculations on that. Setting this up right here, we're simply taking the value B2. B2 is, you'll notice they're color coded there. So the B2 is this cell right here, which is the total number of hydrogens that have been calculated. And we're dividing it by $A, $2. The dollar sign means simply always go to A, always go to 2, or always go to A2 to get this value. You don't ever want it to change from this cell. So whenever you click on a particular cell, you can see the formula up here. We're always dividing by the total of the number of molecules, which of course is what you're going to want to do if you're going to calculate the percent. We've simply represented these all as percentages by choosing the percent feature right here. So if you click on this, you can have the opportunity to select different formats, and we just have selected here the percent format. Now with this row right here, we have contrasted this first row, which is basically the element names, with the percentages, and we now have plotted that out as a pie chart. So you can see right here, the students will come to this point and see, wow, okay, that we only see 4 different atoms represented, 4 different elements represented in most of these biological molecules. It's rare to see a different element, but basically it's going to be, hydrogen is going to be the most abundant by number. Then you have carbon and oxygen with a minor amount of nitrogen. So looking at this, you're going to see that what the textbook says, that basically that biological molecules are primarily made of carbon, hydrogen, and oxygen, and to a lesser degree nitrogen, certainly holds true. But the difference is that rather than just being told that, they have now discovered it on their own. And of course, there's many different investigations they can pursue past this point. For example, they could look at the various different classes of molecules to see if indeed there's any difference between those. So right now we have simply looked at everything in terms of just collectively, but you could compare vitamins and amino acids with pharmaceuticals and sugars, and so you could do a comparison that way as well. We won't here for sake of time. But I think you get the idea that, again, CSCS allows you to do these collaborative investigations that really can take a fraction of the time of a regular investigation. And students can start to learn the value of pooling their data, looking at big trends and big patterns, and seeing things that otherwise wouldn't be so visible. Now it's time to try it on your own. Go ahead and find a molecule and follow the procedure.